Hello, math fans. Been thinking about an interesting problem about putting a cube on its point. In doing so, I've had to do a lot of rotation, a lot of working with vectors, and I thought I could say a few things that might be of interest to my Calculus 3 students, would introduce kind of a fun problem, and would show you, get to review a little bit about how vectors work. Also, I'll get to talk about rotation and how you can do rotation, which I think is fun. I do want to say this problem, what inspired this problem is I was visiting a high school innovation lab, and instructor there, Matt Fluster. Thank you so much for sharing this problem. But mostly I want to talk about the rotation aspect, as I think that could interest students a little bit. Okay, so didn't mean to show you that yet. So here we go. So we have this cube. I've put it on its side. I'm going to do a few things here with it. But before we get started, you can see I've done a lot of maneuvering. I just thought that was fun. So you can see I've put it on its side so that the point is at the bottom and the diagonal point is on top. There's some interesting things. When he first gave me this problem, I was not even visualizing it right. So I just thought it was fun to make that. So I really was determined to provide that picture. And at the end of this, I'll say a little bit about the actual problem. I'm not going to solve it. I'm going to leave it as an open question for you. But I just want to say a little bit about how I got to that point. Now, there's a whole bunch of software packages that would do this, and I'm not an expert on those. I typically do things hands-on. So I'm going to show you a little bit what I did. Okay. And in doing so, we'll get to talk about some interesting things from Math 126 and rotation facts. So I'll talk about what I have up there in just a second. But here's this cube. I've labeled the points. I've put them in 3D. This is the x-axis. This is the y-axis. This is the z-axis. For students that are taking Math 126 or will be taking it from me in the future, we talk a lot about these things in Chapter 12 of Math 126. And it's often a point of confusion. So let's say a few 2D things first. So imagine you have the x, y plane, and you want to rotate points. And then we'll get to vectors, and we'll actually do a problem that we do in our homework that has to do with vectors. But I just would like to rotate. So for example, let's say I would like to take all these points in 3D and rotate them 45 degrees this way, so that, which is actually what I did, so that my cube would be lined up on that plane. I rotated it that way, and then I rotated it up. That's basically how I did it. Okay, let's just talk about that for a second. How would you rotate this way? It turns out there's a cool way to remember it. So I'm just going to take a moment and say this. And if you take linear algebra, you'll study it again. But this is this so-called Euler's formula. This is how I always remember it. And you'd have to take a course in complex analysis for some of the pieces, but it is a very useful interpretation and a very helpful use of the symbol I. This causes a rotation of angle theta. What do I mean by that? If you take these points and rewrite them as if they're complex numbers, I know this is sounding like a lot, and this is not really needed for Math 126. I just couldn't help myself here. You can multiply times this. It's surprising that this works so nicely. And what I mean by that is, so this point, when I rotate it up, you could ask yourself, where is it going to end up? And you can think about the fact that it's not going to end up at 1 because the distance here, you might think about what it is before I do this. So we want to rotate it 45 degrees. I just couldn't help but say this. Again, this is not part of Math 126, but you get the square root of 2 over 2 plus I times the square root of 2 over 2. And if you multiply that, so this thing, we're going to multiply it by this, 1 plus I. Turns out all the arithmetic works out right. So you just define I times I is negative I. And there's a cool bit of complex arithmetic. So this is a very surprising fact when students first see this. So the I times the I is negative 1. And so I did those two things. I called this a monkey face. We just did the eyebrows. There's the eyebrows of the monkey's face. All right, let's keep going. And then we have plus I times, so I times, make sure I still can see what I'm showing you, square root of 2 over 2. That's the nose I just did. And then there's another square root of 2 over 2. That's the mouth. When you're all done, you get 0 plus, let's see, square root of 2 over, okay, so you get I times the square root of 2. And that's the point you get to. I mean, that's pretty miraculous the first time I thought when I saw that. That rotates. Now, more generally, you can do that for any angle. So this is what I'm using when I'm rotating pictures. Now, I know a lot of software packages do that for you. I do everything by hand. It does give me a lot of flexibility. I am going to need to upgrade and get a computer programmer to help me. But every time I'm showing you animations, I'm rotating them using this. Okay, so I'm now going to say one other thing. So that's just a 2D rotation. If you go on into Math 224, you'll talk about rotation more. You'll talk about spherical coordinates. But I think that basic idea is very helpful. So I wrote up something. I'm going to pull it up here. Make it a little bigger. So in general, you can take any point. Here's the x value. Here's the y value. You can multiply it out, and you get the following. The x value times cosine minus the y value times sine will be the new value. And we can write that as a matrix. If you don't know what matrices are, that's fine. This will give you the new x value. And the new y value you get by this. So we call this the rotation matrix. And it's helpful when you're doing various angles. Now in our case, I'm doing 45 degrees. So I took every one of these points and I ran it through the rotation matrix. I did this by hand. Math people watching this are going to be like, he did? Oh, so I took each one of these points and I just ran this. I put the x value here. I put the y value here. And I computed the new x value. I did it by hand because I wanted to show this. And these were the points I got. And that rotated them all. And I'll show you that. Let's go do that. It's a very nice physical chance to see this. Okay, so I'm going to get rid. Let's get rid of my cube for just a minute. It's slowly vanishing. You can see how I drew it. Again, I do everything by hand. Somebody's going to say, oh no, that can't be what he does. Okay, so here's the points. Put them here. And I'll show you them in a second. So there's those 8 points we started with. And then I started to rotate them. Clunk. There they are on the y-axis. So if you viewed from above what I just did, I rotated them. Pretty cool, I think. So there they are. There's the cube. It's just been turned. And then I was like, now I want to rotate it up. I'd like to get that point on the far end up to the top. How am I going to do that? So it's a little exploration of rotation. And this brings me to a separate question. You might have already asked, how did I know that was 45 degrees? I'll let you think about that. But that vector, so I'm going to now I'm going to switch to Math 126 because this was a question you had in Math 126. Let's find some vectors that represent a few of the sides. A, B. Now that's the vector. So it's going from this point to this point. So it's 1, 0, 0. And then let's look at A, H. This is what got me to want to make this video because this is a problem I always get asked in the beginning of Math 126. We don't spend much time on it, but here's an application. Okay, so we're doing A, H. Oh, H is, there's a 1 here. I miswrote it. 1, 1, 1. Actually, you know what? Let's use the point because in the moment I'm going to rotate up. I would really like to rotate up this much. So if it works to use AB, but I'd like to make it look here. So I'm going to use AE. You might think about how that would change things. 0, 1. Okay, so this is for my Math 126 students. How do you find the angle between two vectors? This is a big fact we picked up. I call it a 10-star theorem. We had this U dot V is the magnitude of U times the magnitude of V times cosine of theta. And anyone who's taken this course from me knows that I put 10 stars around it, and I point lots of arrows at it, and I just say, hey, this is the big way we use the dot product and how it comes up. It gives us an indirect line to the angle, which comes from the law of cosines. We talk about it in class. I call this the 10. When someone says, what's the dot product? There's a lot of things you can say. But one thing you say is, it gives us this relationship. And when we use this, the two vectors have to be so-called tail to tail. What I mean by that is the angle that this is talking about is as if they're drawn tail to tail. So I've just drawn two vectors that are tail to tail, AH and AE, and I want to know the angle between them. So here's an immediate application of this. This is the question that you get asked in one of the Math 126 problems. It says, what is the angle between the main diagonal and one of the sides? It turns out it doesn't matter which one of those sides you use. You get the same answer. But let's do it. So we're going to do the dot product of those two vectors, which is just 0, 0, 1. So the left-hand side is 1. The right-hand side is the length of this first vector, and the length of AE is 1. And then we have the length of AH, which is the square root of 3. So you get the square root of 3 cosine of theta. And so you get cosine of theta is 1 over root 3. And sometimes people get confused because sometimes we just leave it like that because that's kind of as pretty as it gets. But you can actually compute it, do inverse cosine. And I did that. I'm going to pull this up here so that we can see it. I'll make it a little bigger. Well, shoot. Let me erase something to give myself some space. The 10-star fact, but you didn't forget it because we put 10 stars around it. How can you forget something that I jumped up and down and put 10 stars around? Okay, 54.74 degrees. It's often better to leave in this form because you can then immediately get what sine is, which I challenge any of my students that have taken Math 125 or Math 126 from me. How do we do that? How do you go from one trig function to another in a quick way? Draw a little triangle. All these little skills maybe have some practical interest. This is square root of 3, and then you can solve for the other side, which would have to be square root of 2. So this is going to be square root of 2 over square root of 3. Okay, if you want to rotate by that much, that's this angle we want. We want to put 54.74 degrees in there, but you just get this number. Oh, I wrote this a different way. I don't know why I rationalized, but you can see that's the rotation I got. This is 1 over root 3. I wrote it in a funny way up in the top right, and here's this value. So these two numbers are the key numbers in this rotation matrix. They're going to be in these spots. Now, I started to do it by hand, then I realized I don't want to do that because it's hard to make the numbers nice. So what I did was I just wanted to show you how you could do it if you wanted to rotate points. I just grabbed an online calculator. I'm going to put 1 over square root of 3 here. I don't know why it didn't make it look nice. And then I think we just said this was square root of 2 over square root of 3, but with a negative in front of it. And then you put this here, and you put this here, and then you just need to enter the point you want to rotate. So let's pick one of our points. How about the 0 square root of 2, 1, and I was just rotating. In that case, in that moment, I was only rotating the YZ plane. I'll show you in a second. So I just rotated the YZ. So I turned everything into a 2D problem. There is a way to do it directly, but I was trying to think about how I was going to do this video. So let's do square root of 2 over 2, 0. And you can hit enter, and it'll tell you what the new point is. And it wasn't nice. It has these square roots of 6. Some of the other ones were worse. But now let's see it. So I'd already moved it like this. There's those points. And then I said, okay, I would like to rotate it up 54.74 degrees. Oh, here it is. And I did the following. So I'm going to put these right on top of those ones. E. One more, E. So there's those points again. And now I'm going to rotate that up. I just thought that was a fun little construction. And then get rid of those other points. I know that there's online things that can do this. But I wanted to use this as an opportunity to talk about vectors, rotations. If you're going to do, I did 3D graphics a little bit when I was in grad school, which is hard to believe. In undergrad, because I was a computer science major, which is hard to believe when you look at this. But this is pretty valuable. There's the points of my sphere. Now at that moment, then I used other skills, parametric parameterizing, because I needed that as a starting point. So let's get rid of this. Get rid of those points. And I use those as my starting points for the problem. Okay, so then I define the sides. How did I define the sides, you might say? Well, because of those points, I can get vectors for each side. I can get a vector for that side, a vector for the next side. And if I have two vectors, then I can walk along those vectors to describe the side, which is exactly what I'm doing here. This is more of a skill in Math 224, but I use those vectors to parameterize. It's called a surface parameterization. Okay, last thing. Then I thought, well, what I really want to do is rotate it. And so from above, I wanted to rotate it again. It's the same thing, the same formula. I'm going to keep all the z's the same and just rotate the x and y. So I'm just using this one rotation formula, and that's how I did this. That's how the software packages are doing it. They're just multiplying by that matrix. I think not that many people know that, so I wanted to use that as an interesting opportunity. You got to see we got to do some vector facts. Very useful if you're working in 3D, these Math 126 tools. Now, just a little plug for the puzzle that I was asked. The puzzle was, once you put it on its side, what can you say about the cross sections? Think about it. Are they triangles? Are they rectangles? Could you find the formula for them? Well, let's see. Initially, what does that look like? And I was starting to parameterize the curves so I could show them to you, and I realized that's too much. I gotta stop. What is that? Ooh, that's a triangle. What's the area of that triangle? What's the volume of that triangular solid? What's the perimeter? Those are the sorts of questions that instructor has the students go through as a challenge question. Okay, let's keep going. Triangle, 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 triangle. At some point we hit that little spot, and then it's something different. And this is the thing I made a mistake in visualizing. Let's look at that. What is that shape? Love that shape. It's like we're filling that thing up with water. If I worked harder, I could make it so it only was right there, but I don't. Now I need someone to give me better software. What is that? It's got these 1, 2, 3, 4, 5, 6 sides. Can we find the perimeter of that? Well, that sounds like a challenge, fun challenge for you watching. Keep going. Let's fill it up. what happens when we get past that upper point? Pretty cool. And then it's a triangle there. All right, let's do, my computer might not like this. Let's rotate at the same time. Oh, yeah. Anyways, thought that was fun to do. And I just thought that was interesting. So thank you for this question. It's still an open question for you. What can you say that's interesting about that? But I thought that was a fun little exploration. I mean, we got to use complex numbers. We got to talk about rotation. We got to do a little puzzle. I did find a way to analyze those cross sections, but it's not easy. You might have to think about it a little bit. If you want to learn more, just search for rotation matrix. That's this. It does go into what this might look like in 3D. Now, when you move to 3D, you have to define where you're rotating from. And so there's different matrices for that, depending on how you're defining your angles. You saw what I did. So here's multiple. This is trying to do it in 3D. It all boils down to the same 2D idea. It's just the order in which you're rotating that you have to think carefully about. I simplified it all by rotating along planes. I rotated in the XY plane, which got me into the YZ plane, and then I rotated up. All right. Hope that's of interest to you. I just desperately wanted to make that picture after that instructor gave me this problem. All right. Thanks for listening.